Stop here. Share screen. All right, we're ready. Did you guys hear me well?
Yes, I can hear you, Professor. I did have a quick question on the lecture videos.
Go ahead.
For lecture number 11, it was just 4 parts, but transitioning from part 1 to part 2, it seems like there was a chunk of material that was missing. You were talking about
exactly. So there is real part 2 is missing, unfortunately. Guys whoever recorded, they don't find it. So anyway, but luckily it was about like something not the main focus. The main focus is the last 3 derivations of MAQ, LP, and NR. So this is the main part of that lecture, and luckily they are okay. But at any rate, I mean, we're going through it today again, and we'll have today's recording. Yes, unfortunately, we don't have this part 2.
Okay, no worries.
So let's start with our usual nice table. This one. Snapshot here. And again, this table is very important. You cannot go through part 2 without knowing the names of our main variables. The velocities U, V, W, or velocity components, the corresponding forces X, Y, Z, and this is aerodynamics and engine, because the gravity is taken care of. It's just mg. Then, so this is the 3 degrees of freedom translational. The 3 degrees of freedom rotational. Here are the velocities. Now they are angular velocities. So these are the components of the omega angular velocity vector, PQR. Then the corresponding forcing, which are moments, because this is rotational motion. LMN, rolling pitch yaw. Euler angles, the angles that the body is making with the horizon, about the 3 axes. Again, roll, pitch, yaw. We learned that if I have a single rotation, so this is indeed phi, indeed will be the roll angle in the sense that its rate of change, phi dot, will simply be the corresponding velocity, p. And the same for theta. If it's only one rotation, then theta dot is q. And if it's only one rotation, then psi dot is r. But when they are combined, then it's a non-trivial relation between the dots of the phi theta psi and the PQR, and you should have turned a homework in this regard. And you did a quiz, and I did a derivation. And you will see it in the final. So in the general sense, when we have 3 simultaneous rotations, Euler angles are fictitious. You don't see them, right? They are angles between intermediate frames. You probably see the very last angle because it's the rotation of the body frame, or to get the body frame. But in general, Euler angles are fictitious. They don't have physical meaning. We don't see them. If we have a single rotation, they are indeed the physical angles between the body and the horizon. Our inputs are simply aileron, elevator, and rudder. So this table is pretty much our taxonomy of variables that we gonna deal with over and over again. And as you guys know, we added last time one more control input, which is the thrust, delta thrust from the engine. Okay, how many variables do we have here? How many unknowns? Like any dynamics problem, I'm given the forces. These are given like forces and moments. And my unknowns are the motion variables, U, V, W, PQR, and the corresponding angles. So 9. So we have 9 by 9 equations of motion. These are the things that we derived before. For example, here is the 9 by 9 actually. Right? So these are indeed rigid body kinematics. I'm sorry, rigid body dynamics. Mass times acceleration equal forces, the first three, and the rotational version of that. Mass moment of inertia times rotational acceleration is the moment, LMN. And then these what we call rigid body kinematics. The relation between our angular velocity components, PQR, and the dots of phi theta epsilon. So these are 9 by 9 equations of motion, 6 dynamics and 3 kinematics, and they are coupled. Look at the first 3 equations. These are equations for translation, right? Mass times acceleration equal forces, but they include angles, theta and phi. They include angular velocities, PQ and R here, in the omega cross V term, in the centripetal acceleration term. So they are coupled. These 3 equations, they have PQ and R in them. And L, M, and N as aerodynamic loads, like M, for example, pitching moment. We're very familiar with the pitching moment. The pitching moment, like any moment, is normalized by 1/2 rho U squared. So it depends on U. So these 3 rotational equations, they have the translational velocities, U, V, and W in general. So these 6 equations are coupled and they include the angle. So in general, the 9 equations are coupled. You have to solve them all together simultaneously. And they are nonlinear, they are differential equations. We cannot solve them analytically, we simply give them to any numerical solver. One straightforward example is MATLAB ODE 45. We will not do this in this class. I mean, you can simply do it on your own. And the result is the heart of a flight simulator. The rest is simply data of airplanes, visualizations, you know, some cosmetics stuff. But this is the meat. Any question about this, about anything that I have so far? And again, please, if you didn't study, that's perfectly fine. Any question?
Yeah, Professor, I have a quick question.
Yes, go ahead.
If this is from the last lecture, if we deflected the ailerons in the same direction, can we use them to generate more lift?
Yeah, you can use them as flaps, and pilots indeed do that sometimes.
Okay, we didn't use them as we didn't use lift as a function of the ailerons last time. That's why.
No, just a second. If you use them together, they are not called ailerons in this case. You will use them as flaps, okay? So ailerons, when anyone in the community says aileron, here is an aileron deflection 5 degree. It immediately says 5 degree, one of them is up, the other one is down, okay? We use them differentially. If you use them the same amount, then they are flaps. They are not ailerons anymore.
Okay, thank you.
You're welcome.
Professor?
Yes, Abdullah?
Is it possible to deflect one aileron, for example, up 3 degrees and then the other one down 2 degrees? Or do they always have to be, you know, same magnitude?
No, you can. I mean, it depends on the airplane. I mean, every airplane is different, but not every, but you can. I mean, many airplanes allow you to do that.
Okay.
But again, in the standard airplane flight mechanics, when we say aileron, we really mean them differential in the sense that if one is positive 3 degrees, the other one is negative 3 degrees. Okay. And when you do really control allocation, sometimes we have luxury in control, like we have many control surfaces, not only elevator, aileron, and rudder. And you want to do, or not even luxury, you have 3, but these 3 are coupled, like something what we call elevon. When it's an aileron, but it gives you, like sometimes in the vertical tail you have V vertical tail, and these V vertical tail, the rudder is used as rudder and elevator as well. So sometimes your control surfaces are not direct as here, Like the aileron gives you pure roll, elevator gives you pure pitch, rudder gives you pure yaw. No, many times they are coupled. You get roll and pitch, for example, or something. So then the what we call control allocation is not straightforward in the following sense. Okay, I want to do pure pitch. How can I do pure pitch? Because when I move my surface, I get both. How can I do pure pitch? So, okay, so you deflect your control surfaces in a certain combination so that the result is a pure pitch, for example. So this is the control allocation problem. So even in the control allocation problem, at the end of the day, you get something that is aileron equivalent, which means it's a differential motion between the right and the left. So anyway, in standard airplane flight mechanics, when we say aileron, we really mean both of them moving opposite each other the same amount, and the same for elevator. When we say elevator 5 degrees, we really mean that both surfaces on the right and left tails, we move them in the same direction 5 degrees, and so on and so. So these are the 9x9 equations of motion, okay? In 9 variables, again, the 9 variables are motion variables, UVW, PQR, and the angles. What should be given is the forces XYZ LMN from aerodynamics. Okay, so they were 9x9 equations, but look what happened last time. Last time when we did the Z-force, recall the Z-force equation. This is what we did last time. Take this up. Let's read the Z-force equation here. It's the last one in the translational version. So it's mw dot plus pv minus qu. So this is mass times acceleration. The first term is pure acceleration. I mean the conventional acceleration that everybody knows, just the rate of change of velocity. And then the second part is the centripetal acceleration. Okay. So this is equal the force. There is aerodynamic force Z, and there is gravity mg cosine theta cosine phi. Okay, and please stop me anytime. Don't ever feel shy if you have a question. Okay, remember last time when we did linearization? So we did linearization. So this equation is nonlinear already. We have p times v. This is multiplication. Whenever you have multiplication, it's a nonlinear term, because when you multiply x by itself, you get x squared, right? It's a nonlinear term. So multiplication is nonlinear. And also we have cosine and cosine, and they are multiplied together. So this is a nonlinear equation. So, and we just approximated it by a linear equation. So we did linearization. And when I say linearization, like we said last time, I cannot stop here. I say linearization about what? So we did linearization about cruise condition. So in the cruise condition, we have some forward speed, u naught. We have some, say, angle, maybe angle of attack, and these are non-zero. Everything else is zero. Like v, little v, which is the side slip velocity, is zero, and so and so. Okay, so we did linearization about this cruise condition. We arrived at the following equation. This was delta w dot. Now, when you do linearization about something, so the resulting equation is in the deltas. Delta mean what? It means the change from this operating condition. I was operating at some forward speed, some angle, and W, for example, was 0, P, Q, R were 0, and so and so. Now this is the change, okay? This was ZU delta U. Again, what is delta U? Is U minus U naught, the change from the operating condition, plus ZW delta W plus U naught plus ZQ delta Q was, I guess, negative G sine theta naught delta theta Z elevator times the change of the elevator from the nominal position, Z thrust times the change of the thrust input. This was the resulting equation. And the derivation from the black equation to the blue, this was like the heart of our topic last time. And you did a similar quiz on this derivation about a slightly more complicated condition. It's not the cruise, it was the pull-up maneuver. The airplane is steadily pitching up with some Q naught. So Q naught was not 0. But anyway, so this is the linearization. Look at this. I want you to look at this now. We started with this equation. It had many variables. It had W dot. Well, I have W dot also here. It had P and V. Well, now neither P nor V exist in the linearized version, in the blue version. They gone. Phi also, it went away. So P, V, and phi, they went away. So the linearization, I started with an equation that has many variables. It has W dot, this is 1, 2, 3, 4, 5, 6, and 7 variables. And you ended up with an equation that 3 of these variables, they went away, okay? This doesn't happen only with the Z force. It happens with all the forces. If you take any of these equations and you linearize it, you will start with a full equation like this, then some of these variables will go away. Okay, so what are you trying to say? I'm trying to say the following, that because the airplane is symmetric, so because of symmetry, about the XZ plane, we talked about this last time, but I want to emphasize it again. So the symmetry and the linearization, when you do linearization about some symmetric flight condition, like the cruise, pull-up maneuver, takeoff, landing, what will happen? The 9 by 9, they are decoupled. They are decoupled into 4 by 4 longitudinal motion. Any motion along the XZ plane. So this is the XZ plane. This is X. This is Z. And like any plane, it has 2 translations and 1 rotation. So the motion here, U, forward speed U, normal speed W, angular velocity about the other axis, which is Y, about Y. Y is into the page, right? So this is Q. And the corresponding angle theta, right? And indeed, in this scenario, because we have only 1 rotation, Q is simply theta dot. So among the 9 variables, 4 of them are here in this plane, U, W, Q, and theta. And this is what we call the longitudinal motion, okay? So the equations of motion here are the X force equation, the Z force equation, the pitching moment M equation, and the last equation is Q equal theta dot. These are the 4 equations in the 4 variables among the 9 again. So the equations and the motion, they are decoupled, they became separate. Any motion along this plane becomes separate from the motion out of that plane. What are the motions in this plane? Like any plane, we have 2 translations and 1 rotation. So translation along X, translation along Z, rotation about the 3rd axis, which is Y, which is not here in the page. So translation along X, translation along Z, rotation about Y. This is the longitudinal motion. So this is this equation, translation along X, translation along Z, rotation about Y, and the 3rd equation would become simply Q equal theta dot. Okay, because in this equation, if you look here, put phi equals 0 and r equals 0, like put all the other motions, all the other rotations 0, you will end up with simply theta dot equals q. Okay, so these are the 4 equations governing what we call longitudinal motion. What is longitudinal motion? It's motion along the plane of symmetry of the airplane. Like here, cruise, for example, any motion that includes these variables only. So cruise, takeoff, landing, climb, descent, but not roll and yaw, right? Not turn, because turn will get you out of that plane. Any question about that? Get this a little bit up. Any question? All right, what is the other motion? The other motion, what we call lateral. So it's the other variables. Lateral flight dynamics, anything out of the XZ plane. Like what? Like the roll rate P, or the side slip V if the airplane is skidding, or the other rotation. Oopsies. The yaw rotation R, or again the skidding V. Okay, so anything that gets you out of the plane. So here we had only one rotation, which is rotation about Y. So here we will have the other 2 rotations. Rotation about X, which is roll. Rotation about Z, which is yaw. Here we had 2 translations, U and W, along X and Z. So here in the lateral, we'll have the other translation, which is about Y, V, little v, the side slip V. So now this is the translation about Y, the side slip, and the other 2 rotations, roll and yaw. Okay, so these are the equations of the lateral dynamics. Again, this will be only phi dot equals P and psi dot equals R simply. Okay, so it's what I'm trying to say is simply the 9 by 9 equations of motion. Now they become a bit simpler. Why? Because of 2 things: symmetry of the airplane, and also linearization, make them linear about some symmetric flight condition, any symmetric flight condition. Look at this, is what we did last time. Going from here to there, the linearization allowed these variables to disappear, or actually forced these variables to disappear. P, V, and phi. P, V, and phi, these are lateral variables. And the equation was an equation for longitudinal motion. This is the Z force equation. Because of the linearization, these lateral variables disappear from the longitudinal equation of motion. And this happens with all the equations. Try any equation you like. So at the end of the day, we have 4 equations here governing these green 4 variables versus 5 equations there governing these 5 red variables. The 5 red variables are, like I draw here, the V, P, R, and phi and psi, right? Side slip, roll, and yaw, simply. Any question about this picture, please?
So you said phi is like an incoming side slip angle to the plane?
I'm sorry, I didn't hear this, Derek.
Was that the phi, like the angles, are those like incoming air velocity, or did you say that's like actual orientation?
Here phi is, after linearization in particular, phi is indeed the roll angle. So phi dot is P is the roll rate, and psi is the yaw angle. So psi dot is the yaw rate. The side slip angle is beta. This is an aerodynamic angle, is different. This is simply the exact definition is sine inverse, if you remember, little v over v. So this is approximately is little v over u naught of the airplane. So beta, this is a good question, because beta, the side slip angle, goes with v, little v, the side slip velocity. So whenever I mention little v, I really mean beta and vice versa. The same here goes with the angle of attack alpha, because also alpha is tan inverse w over u naught, or w over u. Approximately, it is w over u naught. So whenever I mention w of the airplane, I really mean the angle of attack and vice versa. Okay, so they are not new angles or additional variables. They are already embedded in the translational velocities, little v and little w. Okay.
Okay, perfect.
More questions about this picture?
Professor,
Yes.
I noticed that you didn't highlight in the rubric the thrust control for either longitudinal or lateral.
That's a very good question. So strictly speaking, the thrust, and okay, so this is also takes us to the controls. So that's fine about the 9 variables. We classified the 9 variables into 4 here and 5 there. Okay, about the variables. What about the inputs? The control inputs, elevator, aileron, rudder, and thrust. So this goes like clearly, because the aileron is mainly for rolling, so it will go with the rolling motion. Rudder is mainly for yaw, so it will go with the yaw motion. Elevator is mainly for pitching, so it will go with the pitching motion. And now, what about the thrust, like Jessica's asking? So what does the thrust cause to the airplane? Will thrust increase the X force? And if it's offset from the CG, it may cause a pitching moment or a Z force. At the end of the day, the thrust really plays a role here in the longitudinal motion. So the thrust is classified. So thanks for asking. Thrust is classified as a longitudinal control variables. So the 4 control inputs to the airplane, the 4 controls, they are classified 2 longitudinal, elevator and thrust, and 2 lateral, aileron and rudder. Okay.
Okay. Thank you.
You're welcome. Okay, so we're done with this. If you did last time, we did this in detail, this derivation in detail, and you did a similar one in the quiz, and there is a similar question in the homework that is due next or this coming Thursday. So we did this derivation in detail from the full equation to the linearized version. The linearized version, they are all in terms of deltas. So what we have here is delta U. I mean, this is important, guys. Why? Because really people, when they have the linearized version, we will continue the rest of the class with the linearized version. And most of the flight mechanics books, they play with these linearized versions. So when any student or flight mechanics engineer take these equations, the linearized equations, the blue ones, and simulate them, and they get the motion as function of time, how they vary with time, how the U of the airplane vary with time. And they find the U of the airplane is, say, between 5 to 10 meters per second. This is really not U. This is simply only the change from the operating condition, okay? If in order to get the full U or the total U of the airplane, the total forward speed, please add to it the U naught, okay? So anything here is simply change from operating. I hope this is clear enough. All
Professor,
right. Yes.
Really quick, can you just refresh my memory? Is ZU, is that the 1 over M times the partial of Z over partial U?
Exactly, Sam,
Okay.
and we will talk about it in more detail today. Yes.
Cool, thank you.
You're welcome. So this is the, okay, so going from the full equation to the linear equation, this is what we did last time. So let me please, you can really do it for any of these equations. So if you do it for the green ones, here is what you're gonna get, and you'll find them in the lecture as well. So let me show you this here, for example, because I can write W dot in terms of something times the variables and something times the controls. This is my variables are U, W, remember U, W, Q, and theta, right? Let me use the green here. So U is a variable, W is a variable, Q, and theta. And my inputs are the elevator and thrust in the longitudinal. So please lump everything multiplying a variable together and lump all the inputs together. So at the end of the day, you will have this kind of thing. Everything multiplying the variables I, U, W, Q, theta. Again, they are all deltas, right? And everything multiplying the inputs together, elevator and thrust. So in particular, this equation in the middle, this is the one that we derived last time, right? So let me zoom again. This is the blue equation above here, ZU delta U, ZW delta W, and so on. So here is ZU times the first one, which is delta U, ZW times delta W. It is just because W naught was 0, so W here is the same as delta W. U naught plus ZQ times delta Q, which is again the same as Q naught, delta Q is Q. And so on. So this is Z elevator times delta elevator, Z thrust times delta thrust. So this is for the Z force equation. If you do it for the X force equation, you get the first row. If you do it for the pitching moment equation, you get the third row. And the last row is super simple and clear. Theta dot is 0 everywhere except 1 multiplying Q. So theta dot equals Q. So you simply lump all of the equations, something times the variables plus something times the controls. I don't know if you have seen state space models in 170 or not. Did you?
I don't. Could you clarify?
I don't think we did.
Yeah.
Something like this.
You mean the state vectors?
Did you see this equation before?
Oh,
AX
yeah.
plus BU.
Oh, yeah.
Okay, very good. So this is exactly on that form. The dots of my variables equals some constant matrix A times my variables X plus some constant matrix B times my control inputs U. And I'm sorry that we have too many U's. So in order to just change the notation, I'm gonna denote the inputs by U tilde. U is reserved already for my forward speed. So U tilde here is my input. Anyway, this is not my topic today. We will review it, whether you know it from 170 or not, we will review it in detail next time or up to the detail that we want in this class. So that's fine. But this is what I'm just want you to know is, or to observe, is that this equation is exactly on that form, ready for stability and control analysis, to apply anything that you learn in 170 and beyond. This is what we will do in the rest of this course. And we can have a similar system for the lateral as well by the other equations. That's fine. As Sam noticed, and you guys can notice here, I mean, we have a bunch of these things that immediately, all of a sudden, they show up last lecture, and what what the hell is that? Like XU, XW, XQ, ZU, ZW, ZQ, MQ, MW, MU. What are all these things that they show up immediately today or last time, and we never saw them before? So this is actually the topic of today, and I'm sorry that we took like 30 minutes to motivate the thing and to have this taxonomy. Let's see if we have a question here. No.
By Sam, you mean Jeremy.
What?
They're just saying like who took credit for what all those equations meant.
Okay.
Yeah.
So, all right. So let's see what are these things? What is ZU or ZW? Remember how they appeared last time. Let's recall how they appeared last time. Let's try to remember together how they appeared last time. Well, how they appeared in the Z force. What is the Z force of an airplane? It's the force in the Z direction. The Z direction is straight downward. So the Z force is simply, and we're talking about aerodynamics, not gravity. So it's simply negative the lift. And what does the lift depends on? We said the lift is function of speed, right? Of course, it's U squared. And angle of attack, like I said, angle of attack to us is simply W, because it's W divided by a constant. And what else? Last time we said it's also function of Q, and today we're gonna see really why it's function of Q. And elevator, of course, because it may increase or decrease the lift. And thrust, if the engine is inclined to the horizon. And on the side, we remember also if we have any function of several variables, x1 up to xn, I can linearize it by writing this function as f naught plus partial f partial x1 times delta x1, delta from the naught, from the operating, yada yada up to partial f partial xn delta xn. So the x's here are u, w, q, and elevator and thrust. So I can expand my z like any function of several variables approximately, because this is a linear approximation, as some value at the operating z naught, which is simply must be the lift at the operating, which is exactly equal to the gravity for balance, plus partial z, partial u, delta u, plus partial z, partial w, delta w, and so and so, right? Partial z, partial delta thrust times delta thrust. And this term, so this term is what we call delta z, right? Because it's like z equal z naught plus delta z. Delta z is here, is all these things. All right, but at the end of the day, when we have the equation of motion, this is the equation of motion, it's mass times acceleration equal forces, and to get the acceleration, I'm gonna divide by the mass. So really all the forces will be divided by the mass. So let's divide delta z by the mass. If I divide delta z by the mass, this is what I will get. Zu delta u, zw delta w, and so and so. So as you guys can observe, Zu is really nothing but 1 over mass partial z partial u. This is 1 over mass partial z partial w. So partial z partial u is how much your z force, which is simply negative the lift, change with the speed. How much your z force, which is the lift, changes with the angle of attack w, and so and so. These, as you can see, they are derivatives, and they are derivatives of aerodynamic forces. So sometimes it's called aerodynamic derivatives, okay? But because they play a decisive role in determining the stability of the airplane, they are really called stability derivatives. So if I want to choose a name for them, I'm talking now about ZU, ZW, Z thrust, all of them, MU, MW, MQ, XU, XW, whatever, anything. All these things that they show up all of a sudden, they are too many. They are, as you can see here, they are simply derivatives with respect, derivatives of what? A derivative is simply a rate of change, right? So they are rate of change of what? My aerodynamic forces and moments With respect to what? With respect to my motion variables, UVW, PQR, okay? So they should be, strictly speaking, they should be called aerodynamic derivatives. And sometimes they are called like this. But most commonly, they are called stability derivatives. Why? Because they really dictate the stability of the airplane, okay? So our objective today is to derive expressions for these guys. And this is too important of a topic. You will be asked in the homework, of course, which is due Thursday. You will be asked in the final. So let's see. First of all, unfortunately, we'll spend like 5 minutes giving the definitions of these things. Then we will see the meat, which is how to derive them. What do you mean about the definitions? Definition like this, exactly this one, like ZU is 1 over mass partial Z partial U. Okay, but we will give it for everything. Like if I have any force underscore any variable, and you guys know by a force I mean X, Y, or Z, of course. By a variable I mean UVW, PQR, right? So maybe here forces, just X, Y, Z, moments, LMN, right? Velocities, or maybe variables, is UVW and PQR, right? So any force underscore variable is like ZU or ZW, right? This is 1 over mass partial force partial variable. This apply to anything. Example like ZU or whatever. You can have YV is 1 over mass partial Y partial V. Anything XQ 1 over mass partial X partial Q. Okay. So I'm sorry, this will be a little bit boring 5 minutes, but I mean, we have to have the definitions. I mean, you can simply go and read them from the book, but I like to include them in the lecture as well. What else is, if we have moments, so moments, any moment underscore any variable is, as you can expect, is partial the moment, partial the variable. And if the force I'm dividing by mass, you can expect that for the moment I'm going to divide or normalize by moment of inertia. But this immediately causes a problem. Why? Because I have only one mass, so that was fine for all the forces, but for the moment of inertia, I have 3 at least. Well, okay, so divide by the one about which you need the moment, which is, so for example, if I have MU, so this is 1 over some I partial M partial U. But then I'm going to ask myself, what is M? M is a moment about Y, so this is IY. I mean, you really don't need to ask yourself because all these definitions are in the lecture or in any textbook. So you don't need to memorize or don't even need to understand. But these are the standard language in our community. So when you read a report, again, from NASA, Boeing, Northrop Grumman, or whatever, or you need to produce a report for these folks, you need to speak this language. All of our airplane characteristics are in terms of stability derivatives. So you need to know what are these stability derivatives, how they are defined. So here, for example, what is LV, for example? So this is again partial L partial V. And now I'm going to divide by what I? Can anyone tell me?
IX.
X.
Exactly. Very good. So L is a moment about X. So we're going to normalize by IX. So this table, really, you guys spend some time to have it in the back of your mind. It's a very important table. What are the moments? What are the forces? Now it's not clear. You have it in the lecture. And the same here if I have, oops. The same here if I have, say, N, whatever, NR, or NP. This is partial n, partial the variable, which is P, and 1 over IZ, because n is about Z. All right, so any force or any moment with variable is fine. So we define the stability derivatives, but as you guys know, these stability derivatives, by the way, they are dimensional, right? Because here, look at one of them, mu, for example. What's that? So I'm dividing a moment by speed and then dividing by mass moment of inertia. Moment by moment of inertia gives you angular acceleration, like radians per second square, and you divide by speed, so the result is dimensional. Okay, so stability derivatives, they are dimensional. They have dimensions. And we like to represent things in a non-dimensional form in order to be able to compare large and small airplanes, right? In the same token. So there are something called stability coefficients, the coefficients of these guys, as usual. Stability coefficients, and let me waste another couple of minutes, give you the definitions of these guys, and then go to the meat. Thanks for your patience. So if I have C, the coefficient, again, so here instead of having mu, I will talk about CMU. LV, we'll talk about CLV. We never are interested in the actual derivative unless we're doing an analysis for a specific airplane. For general analysis, we always talk in the language of a coefficient, C, okay? So if I have C, and again, too many underscores, force or moment, okay, force slash moment, underscore some linear velocity, like UVW. This is what? This is defined as partial C, the force or the moment, partial the velocity, and you can see it here clearly. C, any C like CL, CD, CX, CY, CZ, the coefficients are non-dimensional. So in the numerator is non-dimensional already. The denominator is a velocity, so it has meters per second. So I need to multiply here by some reference velocity in order for the result to be non-dimensional. And the reference velocity is simply U naught. So that's easy. So example, CXU is partial CX partial U, and I multiply by U naught. CLV partial CL partial V, and I'm going to multiply by U naught, and so and so. Okay, any force or any moment, partial any velocity. All right, the angular velocity is a little bit more intricate, and so if we have C, and if I have any force again or moment, subscript Q, for example, this is what? Partial C, the force or the moment, partial Q. And again, the numerator is non-dimensional, the denominator is radians per second. So I need to multiply here by a reference angular velocity kind of thing. Okay, so it's if I multiply by U naught, so I need a length, because U naught is meters per second. I need to divide by a length in order to have it per second, like this one, and we're done. What is the reference length? Here the community choose half the chord. So this is the standard definition. So CMQ, which is very important one, and we're gonna know its meaning next time, or yeah, next time. It's a very important thing. It's the twin of CM alpha. If you should be obsessed with CM alpha, this goes second, CMQ, and we're gonna talk about it in detail next time. Okay, let's apply this definition to it. So CMQ is simply partial CM partial Q, and you simply multiply to U naught bar C bar. Again, it's just a standard language, and you have these definitions at your disposal. The last thing ever, if I have C force moment, but not Q, I have the other angular velocities like P or R. It's the same, partial C force and moment, partial P or R. And we can also multiply by 2 naught over. And as you can might expect whenever we're talking about lateral rotations, roll or yaw, P or R versus the pitch, the reference length becomes B, not C bar. That's it. So here, if we're talking about C LP, this is partial CL partial P 2U0 over little b. CNR partial C N partial R 2U0 over B. And sorry for this boring thing. Let's go to the meat. But these definitions, I mean, it's our language, you know, you need the language to talk. All right, let's see how we get, so these are too many things. So here alone, how many ones do we have? Here alone, we have 9, and we have like similar 9 for the lateral. And we have 6 for the inputs, and we have similar 6 over there. So this is how many? 9 and 6, 15, and 15 is 30 stability derivative. You cannot, and for each one of them, we have contributions from wing, tail, and so on. So vertical tail. So you cannot memorize these things. You have to really understand how you derive each one of them. Okay, and it makes you understand airplane flight mechanics in a more rigorous or a more fundamental way. Let's talk about the first one. So our first derivation. Let's find or derive CMQ. And again, this is just to give you an idea. This is really not very different from what we have been doing so far in the first half. We were talking about CM alpha. What is this? C stands for coefficient, right? And please pay attention here. Let's start fresh now. Let's ignore all what we had for this, 55 minutes, and let's start fresh, please. This is what I want you to get out of this lecture. CM alpha, this is what we spent the first half of the course with. C stands for coefficient, is nothing, right? M alpha is a moment due to alpha. If the airplane changes its angle of attack, a pitching moment will naturally arise without the interference of the pilot or the autopilot. Okay, so this is the meaning of CM alpha. The exact same here. C stands for coefficient. Just ignore it for the moment. It's just to non-dimensionalize this thing. What is this thing? It's MQ. Okay, what is it? If the airplane experiences a pitching angular velocity Q, okay, and a pitching moment M will naturally arise without the interference of the pilot or the autopilot. And we need to know what is this. Similar to CM alpha, there were contributions from wing, tail, and so on. So here also we have contributions from wing, tail, and so on. So here we're going to find CMQ due to horizontal tail. Let's do this together. So this will be the question in the final or in the homework. Find the contribution of some component of the airplane to one of these stability coefficients. Again, I'm stressing that this is the disturbance. Q is the disturbance. And M is the output. So this is in your mind. So we're going to apply this disturbance to the airplane and see the effect of this disturbance on the component under study, the horizontal tail. After we get that, the effect on the component, we see, okay, what output do you want? You need the moment, pitching moment out of that. Okay, let's get it. So how do we start? We're going to apply a disturbance Q to the airplane. And here the table is super important because what is Q? I cannot solve this problem without knowing what is M and what is Q. Q is the pitching angular velocity. M is the pitching moment on the airplane. So I'm going to apply a pitching angular velocity. Okay, Q is about what axis? Q is about the Y axis. So in order to draw this and for Q to appear, for any rotation to appear, you sketch the plane that doesn't include this axis. Again, Q is a rotation about Y. The only plane where this rotation will appear is the XZ plane, the plane that doesn't include Y. So let's sketch the XZ plane of the airplane. Here is our lovely XZ plane. Here is the wing, the CG of the airplane, and what component you want. We need the effect on the horizontal tail. Well, here is the horizontal tail. All right. We need to apply a disturbance Q, and we always apply it in the positive sense. So remember, this is really x-axis of the airplane. This is Z, so Y is into the page. And if Y is into the page, please put your thumb of the right hand, of course, into the page, gives you the positive rotation about Y. And we know this from before, the positive pitching is upward. So this is the disturbance applied, Q. It's an angular velocity, omega. So the points ahead of the CG will go up with some speed, and the points behind the CG will go down. The airplane as an entire body is rotating about the CG with this angular velocity Q. Any question about that? Any questions? Do we have questions in the chat? I don't know, don't have access. All right, so what is the effect of this angular velocity on the component under study, the horizontal tail? That's easy, because this distance, we know it from before. What's this distance? This is L tail, right? So omega R kind of thing. If you have a body that is rotating by an angular velocity, any point offset from the center will move. So the entire horizontal tail will move down by a tangential velocity omega R, or my omega is Q and the radius is L tail. So this is the velocity, the downward velocity of the horizontal tail, QL tail. Anyone has an issue that the tail will go down? If the airplane is rotating, the tail will go down by this velocity. The rest is easy. Why? Because if the tail is going down, what happens? Here is the horizontal tail. Initially, it was moving with a velocity u0. Now I added this velocity QL tail, right? So this is the resultant. And if this is the resultant, this is what? This is the change in the angle of attack, right? This is alpha. This is the change in the angle of attack on the horizontal tail, alpha tail, right? Delta alpha tail, which is how much? From this triangle, it's exactly equal tan inverse the blue over the green. And as you guys know, we always neglect the tan inverse, so it's approximately QL tail over u0. Any issue about this? Any question that this is the change in the angle of attack on the horizontal tail due to the disturbance Q? Guys, this is important. I mean, and we start from here, irrespective you understand anything from before or not. So starting from here, find CMQ due to horizontal tail. We're following together. I don't care if you studied anything from before or not. If you studied anything, lecture 8, 9, and 10. This is new stuff. Anyone has an issue that if the airplane is rotating by this blue Q, then this will be the change in the angle of attack on the horizontal tail. Because the rest is easy. The rest is turn the crank. Why? Because if any surface, not only the tail, experiences a change in the angle of attack like this. By the way, the change in the angle of attack is positive or negative? Like the angle of attack increases or decreases? The angle of attack increases. Why? Because the surface itself is going down. So you can make the usual trick, which is keep the surface stationary and have the air coming in the opposite direction. If the air is coming in the opposite direction, then the air is pushing from below, so it's pushing up, so the angle of attack increases, and I will have increase in the lift. Okay, so now I managed to characterize or to simply determine the effect of my disturbance on my part of the airplane, the disturbance Q on the horizontal tail. It's just the final result is an increase on the lift by this amount. All right, what output do you need from me now? The output is the pitching moment. Okay, go and get the pitching moment due to this effect. That's easy, because pitching moment about what point? Of course, about the CG. So here is the moment arm again, which is L tail, exactly L tail. So this force will be multiplied by little L tail, give you a pitching moment in that direction, which is negative because it's opposing to Q, and I assumed Q in the positive sense at the beginning. Any question about that? So let's write down these two lines. What are these two lines? Well, delta L tail will give you change in the lift force on the tail. Like anything, this is 1/2 rho V squared. This is on the horizontal tail, S tail, and the change in the lift coefficient is simply CL alpha delta alpha. Right? So this will go here. And now, what is the moment? Moment is this delta L tail multiplying with the moment arm, little L tail, and this is a negative. And please, please don't let any of these lines pass. If you have any little, no matter how small the issue is, just stop me. This is very important. So let's substitute. This is negative 1/2 rho V squared, tail S tail, CL alpha tail, and delta alpha coming from above is QL tail over U naught, and I have L tail from here. And as you guys know, whenever interested in the quantity, we always normalize. So we're gonna divide both by 1/2 rho V squared S and C bar, because this is the pitching moment M. We always normalize by C bar. And you guys are experts on this, because now when you divide the moment by this, you get the CM. Here is the negative 1/2 rho V squared tail over that of the wing gives you eta tail, S tail over S, L tail over C bar. And what else? I still have QL tail over U naught. I managed to get CM, the moment coefficient, due to the disturbance Q. Now I need a punchline to finish this derivation. The punchline is in the list of definitions. How you get CMQ? Well, in your expression for CM, please differentiate with Q. It's gonna be always linear in Q, something times Q. So this derivative will be the coefficient of Q. Take it and multiply it by 2U naught over C bar. So CMQ is 2U naught over C bar partial CM partial Q. And as you can see from here, partial CM partial Q is indeed everything multiplying Q, right? Because this is linear in Q. So now we're done. CMQ is negative. Here is the 2. When you multiply U naught by U naught, they go away. And I have eta tail. And you guys also are expert that this collection is simply VH, right? And oops, L tail over C bar. This is CMQ. Any question about that? Because you're gonna do this over and over again. I'm gonna do 2 other examples for derivations.
There was a question in the chat about the subscript T for the dynamic pressure, 1/2 rho V squared.
See here.
It's in the N equation.
Yeah. Because this is the here, this is the lift where? This is the lift on the horizontal tail. So it's dynamic pressure at the horizontal tail, correct? This is our usual way of doing it. If I'm at the wing, if I'm considering, like next example, I'm considering something on the wing. Well, so it will be 1/2 rho v squared on the wing, which is the same as that of the airplane, right? The airplane reference is the wing. And after the last example, I will do something on the vertical tail. So this will be 1/2 rho v squared at the vertical tail. It really depends on the component that you're considering, right?
Right. And so when we normalize and we divide by 1/2 rho v squared, that's for the reference for the.
This is exactly, this is reference. So this is irrespective of what component you're considering, because now when we're normalizing for a reference for the entire airplane. And the reference for the entire airplane is chosen by the community to be that of the wing. So all these things in the numerator will be that of the wing. So if I'm considering wing stuff, these things will cancel with each other, right?
Okay. And the eta tail term is the representation of that, right? It's Q.
Yeah, it's the ratio between 1/2 rho v squared on tail and wing. This is the same as our eta tail that we had in the first half.
Professor, what happened to the CL alpha?
Oh, thank you. No, it should be there. Where is, let me get it. CL alpha, where did I forget? So here, let me have this. All right, I have a room. CL alpha tail. I was feeling like there is something missing. CL alpha tail here. Thank you, Ethan. More questions?
So in the final expression for CMQ, do we not do that thing that we did in the first half of the course where we say that contribution to, from the tail?
This is contribution from the tail only. Yeah, I mean, you can, thank you. If you wanna, I mean, if you wanna stress, this is indeed delta tail CMQ. Yes, but it was because this is the question is only asking about this. But yeah, strictly speaking, this is really the tail contribution. More questions? Second example is CLP due to wing. Let's start fresh, do this together. What do we mean by CLP? Well, C is just a coefficient. Trash it away. It doesn't have any meaning. It's the coefficient of LP. Okay, what is LP? So P is the disturbance. Let your airplane experience a disturbance in P. What is P? Please go to the table. P is your roll rate, right? We have PQR about the XYZ. So P is the rotation about X is the roll. So if the airplane experiences a roll disturbance, I need the resulting L out of that. What is L? L is the roll moment. Okay. So this is the output. So please go and allow your airplane to experience a disturbance or roll disturbance P. See how this affects the wing. And from this effect, please get the output, which is the roll moment. So let's do that together. How to start, because this is super important. The sketch is very important. You need to see, to determine what view to sketch. P is a rotation about X. So immediately we draw or we sketch the plane that doesn't include X. So the X, the YZ plane. So let's sketch the YZ plane. Here's our wing. And here is my disturbance P. Again, let me, so far I don't know really, I have to specify the axes. So this is, if this is Z, Where is my y? Choose your y. If your y is to the right, then this determines that x is into the page, because my y is always to the right wing. So my x is into the page, and if x is into the page, please put your thumb into the page. This gives you the positive rotation. So here is the positive rotation, P, okay? So I allowed, yeah, go ahead.
We always assume it's positive into the page.
Yes, exactly. I allow the positive disturbance, and the output comes naturally, whether it's positive or negative, I don't care. Okay, so now I ask myself, what is the effect of P on the component under study, on the wing? Yeah, I mean, again, this is a body that is rotating about a point. So all the other points will move either up or down. So, but the issue is that the wing is very large. So a point on the tip will move down with P multiplying by all this distance. But a point near here in the root will move just very little. So the results will be very different from one point to another on the wing. So this is encouraging to chop your wing into stations. So I'm going to take, as usual, station of width dy and at a generic y. For this particular station, how much it will move downward? Well, it's the omega times the radius. My omega is P, the radius is Y, right? And this airfoil section, oops. Here is the airfoil section. It was moving horizontally with a speed u naught. Now I'm adding to it P times Y. The result is a change in the angle of attack on the wing, right? So the change in the angle of attack of the wing at this station Y is approximately how much? Can you tell me from this picture?
Py over u naught.
Exactly, Py over u naught, right? It's tan inverse, but we just ignore the tan inverse. So it's typically this scenario. It's typically the disturbance over the forward speed. Any question about this so far? That when the airplane rolls, the right wing moves down. And when the right wing moves down, then it's as if the air is pushing from below, so increasing the angle of attack by this much. Any question about that? And if the angle of attack increases, what will happen on the lift on that section? The lift simply increases. So this is delta lift on of the wing at this y, right? So this is delta left wing at this y, simply here 1/2 rho v squared, no subscript. This is the wing. And then times the area. Well, unfortunately, I'm not taking the entire wing. I'm just taking a slice of it. So it's just C times dy, the area, the chord times dy, as we always do. And then, so 1/2 rho v squared area times CL alpha wing times delta alpha wing at this y. So this comes right away. All right, so the effect of this disturbance on my wing is an increase of the lift on the right wing, and of course it's decrease on the left wing. Okay, now what is the output that they are asking about? The output, they are asking about the roll moment. So from this effect, how you get the roll moment out of that? How we get the roll moment? We simply multiply by this distance again to get the roll moment, large L, which is, as you can see, it's also opposing to P, and P was positive, so L is negative. So what is L from this sketch? It is the change in the lift force, this Y, times the moment arm. Can anyone suggest what is the moment arm?
Why?
Why?
Exactly, and it's in negative. So let's simply substitute and we're done. So this is the lift is, or the, I'm sorry, the rolling moment is negative 1/2 rho v squared. And let me, this is, we're not done yet here actually. Why? Because this is just due to one station. So I need to sum all of them. So from 0 to b over 2, and since it's anti-symmetric, I'm going to just have half wing and multiply by 2, right? So let's do that. So I have my L is -2. Anything that is constant, doesn't change from one station to another, I'm going to get it outside the integration sign. So 1/2 rho v squared doesn't depend on the station. They all moving with the same speed. You can have v squared or u naught square, whatever you like. CL alpha wing, I'm going to get it outside, and this now becomes large L because it's for the entire wing. What else? The chord, of course, has to stay inside because it's function of y, really, for a tapered wing. This is P y over u naught. So P and u naught is the same. I mean, don't depend on y. And there is another y here, another y here. So this is times y squared dy. And this is from 0 to b over 2. Right? So I managed to get the rolling moment. All what I need now is simply do the normalization, 1/2 rho v squared area, and this is a roll moment. So please remember that it's b, not c bar. When you do that, you get the roll moment coefficient from here. And here you guys see this. This is, they go away, 1/2 rho v squared with 1/2 rho v squared. So what do we have? We have -2 CL alpha wing. And this integral, you can get it from you will find it in the lecture notes. Look at this. You will find here in the lecture notes that integral of cy squared okay. So integral cy squared is simply c root times b cubed 3 lambda plus 1 over 96 something. And also the area is, this is little detail. You're not always required to do that, but it's if you want to finish the derivation in a clean way. So this is c root b lambda plus 1 over 2. So now you can have things, this is that. So you can have things cancel with each other, like CR b squared with CR and b cubed. So what you end up with is there is b on above, I guess. There is 3 lambda plus 1 and lambda plus 1. There is 96 and divided by 4. This gives you like 24 or something. I mean, do it on your pace. It's super simple here. It's nothing fancy. Let me see, there are questions in the chat. Y squared, there are two y's. There is y in the angle of attack, and there is y in the moment arm. When you multiply all together, you get y squared. Anything else I'm missing from this expression? Yes, I'm missing P and U naught, I guess. I hope this is, yeah. All right, so this is the roll CL, the roll moment coefficient. We don't need the roll moment coefficient, we need CLP, CL due to P. This is really CL due to P. We just need the coefficient of P, right? So please go here to get the definition. So differentiate your CL with respect to P, i.e. get the coefficient of P and multiply by this guy. And we're done. So this is CLP is 2U naught over little b partial CL partial P. So this is negative CL alpha wing over, when you multiply by 2, this becomes 12. And when you multiply by U naught, this U naught goes away. When you divide by little b, this b goes away. And you just end up with 3 lambda plus 1 over lambda plus 1. Lambda is the taper ratio of the wing. And we're done. Any question here? Aside from these integrals, again, you will have them at your disposal. Any question about the idea, the derivation?
Yeah, Professor, I'm having a hard time understanding why the angle of attack increases. I mean, I get that if the wing is going down, then you'll essentially have air pushing the wing back up. But since the angle of like the plane of the wing isn't changing with respect to the forward velocity, I don't see how the angle of attack changes.
It is changing with respect to the forward velocity, right? Now, look at this picture. Originally, without the disturbance P, without the blue velocity, we have simply U naught. So assume that this U naught is aligned with the chord. This is the chord. So the angle of attack here is 0 originally. So the wing is moving straight horizontal with, say, 0 angle of attack. Now, after applying P, if the wing, in addition to moving horizontally, is also moving downward with this Py, the resultant airstream, the resultant velocity of the wing, what's the resultant velocity of the wing? Is the addition of these two vectorially, the resultant of these two, which is the purple. So now, to me, this whole section is moving with this purple velocity. What is the angle of attack? It's the angle between the velocity and the chord line, which is horizontal. Okay?
Okay. Yeah, that makes sense. Thank you.
You're welcome. To visualize it a little bit better, you can always, as you know, keep the wing stationary and have the air coming in the opposite direction. Indeed, when you have the air coming in this direction, there is a positive angle of attack. More questions? The last example. We'll do CNR due to vertical tail. Again, what's my disturbance? Here is disturbance. What is the output? Here is the output. Okay, how to start? Well, what is R? What is my disturbance? My disturbance is a rotation. It's one of the rotations, PQR. And it's the last one about the z-axis. So if it's about the z, then it will show up in the xy plane, the plane that doesn't have the z. So let's sketch the xy plane. So this is
Really quickly, Professor, can I
yes.
ask you a question regarding the last example?
Yeah.
Sorry, not to hold us back, but like when you took the derivative, partial CL, partial P, it's -1 over 12. Why isn't it still, why not -1 over 24?
Because there was a 2 here. The definition of CLP, you get the CL, differentiated with respect to P, so remove B, and then you multiply by 2 U naught over B, so you multiply by 2. So this 24 becomes 12.
Oh, okay.
There's 2 in the definition. In actually all these definitions of the of the rotations. The CMQ, CLP, CNR, all these rotations, there is 2.
Right.
Says
Okay.
the reference length is taken to be half of these things. So this is the XY plane, and I'm sketching the XY plane because it's the plane in which the yaw rotation will show up. Again, if this is X and this is Y, remember Z of the airplane is straight downward. So straight downwards, it's also into the page. Please put your thumb of the right hand into the page. It gives you the positive rotation. This is the positive rotation, R. It's as if the airplane is yawing with this velocity. What's my component? My component of interest is the vertical tail. Here is the vertical tail, and I'm exaggerating its size a little bit to show up. All right, and as you guys know, if you remember, this distance is really little LV. So what does this disturbance R do to my surface, the vertical tail in purple? Well, it will move sideways, right? With what speed? Again, it's the angular velocity R times the arm. The arm is LV. Any question that if the airplane is yawing to the right, the vertical tail will move to the left with this velocity RLV. And if this is the case, can you tell me firsthand what is the change in the angle of attack on the vertical tail without doing too much work? Can anyone tell me that?
You said our LV over
U naught.
Exactly, over U naught, exactly. So it's the disturbance over the initially forward speed. So this is the change in angle of attack on the vertical tail. Anyone has an issue with this? Does anyone has an issue with this? Because remember, this thing was originally moving with U naught here, right? Now it's in addition moving down. Actually, it's not down, it's to the side with RLV. So the change in the angle of attack is simply tan inverse of the ratio. Any question of this first statement? Because as you guys know, I mean, from this first statement, everything follows down naturally. You just turn the crank. Change angle of attack causes a change in the lift, and the lift you multiply by a moment to arm to get the moment. Do non-dimensionalization, we're done. So this very first statement is quite important. Do we have something in the chat? Sometimes I don't have access. Yeah, here. No, that's okay. I have my kids fighting all the time, actually. So let's see. Any question about delta alpha V? Guys, please. All right. So delta alpha will, if the surface changes the angle of attack, I will get change in the force. And now you ask yourself, I keep saying this, and I don't think that you guys feel it. I keep saying that, okay, you get the effect of the disturbance on the surface under concern. And now you ask yourself about the output. Because really, sometimes the output is not what you think. Here, the output is natural. What's the output? Is the yaw moment. Okay, so how do you get it? Well, we multiply this lift by the same distance again, which is LV, to get a moment N. So my moment N is simply the change in the lift times little LV, and as you can see, it's negative. Yes, but this is not always the case, because sometimes I have, where should I? Maybe here. Oops. Here is the vertical tail. And okay, here is the force. So I got the force, fine. And I multiply this force by little lv to get the moment. If I want the yaw moment n, but what if you're asked to get CLR? Then the output is not n, the output is the roll moment L, which how you get it from this lift force? Well, we get it by multiplying with this vertical distance. If this is the axis of the airplane, right? And this vertical distance, we call it ZV, okay? Like we have LV here and ZV. So it really depends on the output, okay? Do you guys understand this?
Professor,
Yes.
I had a question. Cause like on the homework, it just mentions like CNP. So that would just be about, how would you go about that though?
Very good. So here the disturbance would be P. You go and do this, and it's due to what? Due to vertical tail, I guess, right? So you get the effect of this P on that guy. It will cause a change in, I mean, there's going to be a side velocity, P times, say, Y, and then you divide by U naught to get the change in the angle of attack on the vertical tail. So you get a lift force, which is a side force on the vertical tail. And now you ask yourself, what's the output? If the output is roll, then you multiply this force by this distance, which is ZV or whatever.
Oh, okay. So we have to like switch like the view kind of.
Yeah.
Okay.
Yes. Sometimes you need to switch the view.
Nice. Thank you.
To get the output. Yeah, you're welcome. Okay, so here in our problem, it's a bit simpler. We got the change in the angle of attack. This leads to a change in the lift, which is, as usual, 1/2 rho v squared. Now it's the vertical tail. S vertical tail, CL alpha vertical tail times delta alpha vertical tail, and this is the delta alpha. And once you have the change, the force, you multiply by the moment arm to get the moment, and let's substitute, and we're done. So what is N? Well, N here is negative 1/2 rho v squared vertical tail, S vertical tail, CL alpha vertical tail, RLV over U naught, and I have another LV lingering. And as you guys expect, what is the next step? Can anyone tell what's the next step?
Normalize.
Exactly. 1/2 rho v squared of the entire thing, SB. So from this, when you normalize from N, you get Cn. This is negative. When you divide the 1/2 rho v squared, you get the eta, vertical tail now. SVLV over SB, CL alpha V. I still have another LV, and I have maybe U naught and R. Then there is a punchline. What's the punchline? From the definitions. Go please and get it from the definitions. CNR is 2U naught over B partial CN partial R. So this is Cn differentiated with respect to R. It's actually linear in R. So which means just get the coefficient. So this guy is simply the coefficient. So CNR here is negative, and we multiply by 2. And you guys know that this is simply VV. And you multiply by U naught, so this U naught goes away, and then you divide by B. This is the, and we're done, and you'll do 10 minutes